Have you ever wondered what keeps a spinning top from falling over? Or, for that matter, what keeps our own planet turning day after day? Well, today we're going to dig into the physics of spin, the amazing science of rotational dynamics. And to get started, let's think about a classic puzzle. You've definitely seen this before. An ice skater starts spinning, kind of slow, with their arms stretched way out. Then, whoosh, they pull their arms in tight and suddenly they're spinning like a blur. How in the world do they do that? They're not pushing off anything. That's the mystery we're going to solve. But before we can figure out the skater, we have to back up and ask an even more basic question. What actually makes something start spinning in the first place? It's not as simple as just giving it a push. The answer is a little something called torque. You know how a force is a push or a pull? Well, torque is the twist. It's the rotational version of a force. Think about opening a heavy door. You push on the handle far away from the hinges, right? That's because you're creating torque to make it swing. And if you want to get the most bang for your buck, you do it just like you see here with this gear. You apply that force as far from the center as possible, right on the edge, and you push in the direction you want it to turn. Pushing anywhere else or at a weird angle just wastes your effort. Okay, so applying a twist is how you get things going, but that's only half the story. Just like pushing a heavy box, every object has its own built-in resistance to being spun. And that resistance has a name: rotational inertia. Honestly, the best way to think about it is just rotational stubbornness. If something has a high rotational inertia, it's really hard to get it spinning, and once it's going, it's really hard to stop. So what makes something more stubborn than something else? Well, it really just boils down to two main things: how its weight is spread out, is it all packed in the middle or spread out wide, and, of course, its overall size. Let's make this super clear. Take a look at these two wheels. Let's pretend they have the exact same weight. The wheel on the right, where the mass is all the way out on the rim, is way more stubborn. It has a much higher rotational inertia, so it's harder to spin than the one on the left, which has all its mass near the center. All right, so we've got the twist, which is torque, and we've got the stubbornness, which is rotational inertia. Now we can finally put them together and reveal the ultimate rule that governs absolutely everything that spins. It all comes down to this really elegant little formula. This is basically Newton's second law, but for spinning things. That first symbol, tau, is for torque. The I is for rotational inertia. And that last one, alpha, just means how fast the spin is accelerating. But let's forget the symbols. All this equation is really saying is that the more twist, or torque, you put in, the quicker the object will speed up its spin. And the more stubborn it is, the higher its rotational inertia, the more twist you're going to need to get it going at the same rate. It's really that simple. And with that, we have all the clues we need. It's time to go back to our ice skater because we can finally solve the mystery. And it's not magic, I promise you. It's just pure physics. The secret weapon here is one of the universe's most fundamental rules, the conservation of angular momentum. It's a fancy term, but it just means that once something is spinning, its total amount of spinness, its angular momentum, has to stay the same, unless some outside twist messes with it. Okay, so look at our skater. When she starts her spin with her arms held way out, she's spread her mass far away from her center. Remember that stubborn wheel with all the weight on the outside? That's her right now. She has a really large rotational inertia. Okay, here it is, the big aha moment. Once she's spinning, her total angular momentum is locked in. It has to be conserved. So what happens when she pulls her arms in? She brings all that mass closer to her center. That move dramatically lowers her rotational inertia. Her stubbornness plummets. But the universe demands that her total angular momentum stay the same. So if the inertia goes down, something else has to go up to balance it out. And that something is her speed. Her rotational speed absolutely must increase. And this is the result. Her arms are in, her rotational inertia is low, and to keep the universe happy, her speed becomes incredibly high. It's a perfect trade-off, dictated by the laws of physics. You see the exact same thing when divers or gymnasts tuck themselves into a tiny ball in midair to spin super fast. Now, this isn't just about athletes. Let's zoom way, way out and see how these exact same rules work on a scale that's almost impossible to imagine. I mean, just think about our own planet. The reason we have a reliable 24-hour day is because of this very same law. Billions of years ago, the stuff that made the Earth was already spinning. And since there's basically no external twist out in space to slow it down, its angular momentum has been conserved, so it just keeps on spinning. In fact, its spin is so incredibly stable that it creates this kind of invisible arrow, a vector, that points straight out of the North Pole, right towards the North Star. The stability of everything we know, our days, our seasons, it's all thanks to this one fundamental law. So there you have it. From a figure skater's spin to the rotation of an entire planet, the same basic rules apply. This amazing dance between torque, inertia, and momentum is happening everywhere. So the next time you see a bicycle wheel spinning, or a ceiling fan, or even kids on a merry-go-round, take a second and ask yourself, what else around me is secretly following these incredible rules?